Thank you, Johanna, and thank all the listeners to be interested in neutron spectroscopy. So you heard about diffraction and small angle scattering already, and we will move now to the point that neutrons will gain or lose energy while interacting with the samples. This technique or this effect probes a quite large variety of different physical phenomena. For sure, the dynamics of the lattice, which is mainly represented by the phonons, but also a lot of other motions of atoms or molecules. And since neutrons are very sensitive to magnetism, for sure you can also investigate magnetic excitations or simply electronic transitions with that. One should know that the lattice vibrations are responsible for a lot of properties of our materials, like specific heat, thermal conductivity, the electrical resistance, or the electric and optical properties. So understanding the lattice vibration or lattice vibrations opens us the world to know about the atomic bondings. It allows us to calculate the atomic forces. And in a second step, for sure, it allows us to tune the material into the way that we can go in the direction of properties we would like to have. And the same is valid for magnetism. If we can understand the interactions which originate the magnetic properties, we also can understand the consequences. So we can manage our materials by understanding how these different interactions either are balanced, how they compete, or how they are coupled. I will start with one of the two main techniques of neutron spectroscopy, which is not the main topic of this talk, and this is the time-of-flight spectroscopy. Technically, you start from a neutron source, and the source normally emits a polychromatic beam. That means that all the neutrons have, or that the neutrons have a quite large variety of energies and also K vectors. And we take the neutrons which come along our instrument direction. And what we want to do is we want to learn now how the neutrons change their energy while interacting with the samples. And a good way is to know the energy which the neutrons have arriving at the samples. And in the case of the time-of-flight spectroscopy, this is done by a kind of chopper device, which allows you to get a starting point of the starting time of the neutron beam, which will arrive at the sample. And by rotating with dedicated planes, it allows you to give a time slot when the neutrons pass this chopper. And this gives you the starting point, and for sure also the direction of the beams, which is represented in our way by an incoming energy and an incoming wave vector. And knowing now the distance between the chopper and the sample, you will know at which time the neutrons arrive at the sample, or vice versa. If you know the time when the neutrons arrive, you will know the energy of the neutrons. Interacting with the sample, the neutrons will create a scattered beam with quite different energies and K vectors. So they come from the sample into several directions. And if we take one neutron, it will have a finite, so-called finite energy and a finite K vector. And if you know now the time when the neutron arrived at the sample and you detect the neutrons with a timestamp, then by knowing the length or the way between the sample and the detector, you can conclude about the energy. And for sure, with the angle, you can also conclude about the Q direction. So what we get finally is we use the time and length correlation to know about the energy of our neutrons. We can cover, if we use a lot of detectors, a quite large Q omega range. So we can get an overview about the spectrum in the E omega dependence, which is quite nice efficiency of the neutrons produced by our source. In addition, we do not need any filters, so we have no attenuation on top. And this method is possible for powders, losing the dedicated information about the crystal direction. But nowadays, we also have quite advanced time-of-flight spectrometers for single crystals. There are a few disadvantages. The technique is not very well suited for quite weak scattered intensities. You need a lot of calibration measurements for knowing about the dedicated intensities of your measurement, which is also time intensive. And you have a quite complicated data analysis, and sometimes you need several corrections to get from your data what you want to know. I have here the sketch provided by ILL at the for the instrument Ion 6 to make it better understandable. You have a polychromatic beam here. You have 3 monochromators. The neutrons go onto the so-called Fermi chopper, and you see that a bunch of neutrons, a short bunch of neutrons, goes through. So you have 3 beams of monochromatic energy. And then after scattering at the sample, in a quite large detector box, you collect all the neutrons with timestamps. And finally, you have here a picture of your scattered neutrons. And with some mathematics and data analysis and data treatment, you get finally intensity over energy for each Q point. The complementary method is the 3-axis spectroscopy, where I was asked to speak about. The complementary will be easily visible during explanation how it works. Again, we have a source where the polychromatic beam is emitted. And now again, we want to choose the energy which arrives at the sample, and we choose this energy by a monochromatic crystal. That means by simple Bragg scattering, which we easily can understand after the talks before. With an incoming energy, which is decided by the angle on the monochromator, and an incoming wave vector, we have the interaction of the neutrons at the sample, and we choose one direction of the outcoming neutrons, put again a monochromating crystal, in this case analyzer crystal, called into the beam, and we choose again by the same principle one final energy and reflect it to the detector under a dedicated final wave vector. So what we easily understand is that we have a point-to-point measurement. Each point is related to an energy transfer between the incoming and the outcoming neutrons. And everything depends on the angles which we can choose between the at the monochromator and at the analyzer. So that means that the resolution and the efficiency depends from this angle measurement. So we select the energies by Bragg scattering. The resolution can be quite high. So the resolution in triple axis spectroscopy is the full width half maximum on the elastic line measured on a standard material like vanadium, and this can start from 20 micro eV in the cold case and goes to 1 or 1.5 milli electron volts and at thermal instruments. The advantage of the measurement is you have a quite easy to understand outcome. You have ASCII data of intensity over energy, or Q. The disadvantages are that you have this point-to-point measurement. You have filter wavelengths, which again give you a loss of used neutrons. It's dedicated mainly for single crystals, which need to have a useful size, and you are restricted to a so-called scattering plane. That means you can measure in 2 Q directions, but the third one will be lost in a single measurement. Normally are single detectors used, but in our days we are going to the development that we try to have several detectors, so we can measure several points in Q at the same time, or we have combined multi-analyzer, multi-detector systems, which allow a little mapping of our Q omega space. The same principle as shown at, for time of flight is here given by ILL for ion 12. We select with the neutrons, we select one wavelength, we scatter at a sample at a selected Q position. We need to pass a filter either before or after the sample, and then we collect the neutrons of the selected energy at a detector. And what you see here, for each measurement point, you need to move the whole instrument around the monochromator. And you easily can see in the sketch also the point-to-point measurement, and you need some time to move the instrument from one point to the other. On the other hand, you get here a more or less Gaussian peak, which immediately lets you know what you are measuring. At MLZ, we have several of these instruments. The classicals are PUMA for a thermal spectrum and the cold spectrometer PANDA. But in addition, these both follow the classical setup as shown before. In addition, we will have soon a fully polarized spectrometer, which is called COMPASS in the cold spectrum. And we have one spectrometer, which is starting to be used for triple axis measurements, which is MIRA. This is, at least at a time, restricted to constant Ki measurements, which on the other hand allows to measure quite stiff excitations. That means quite large changes in energy with small changes in Q, and mainly at low Q, like ferromagnetic spin waves. So it's in some case complementary to the other instruments, and therefore an excellent partner in the suite. So what do we measure now, or how does it go, and how do we perform the measurements away from the technical point? You have the phonons, which are quantized lattice vibrations, which means you change the energy of your excitation when you go through the Billerand zone. You need to take into account the polarization of your vibrations, either along the Q direction or perpendicular to the Q direction, which easily leads you to the understanding of longitudinal or transverse phonons. And what you finally do is you measure now point for point, starting at a lattice vector G and adding a small vector, so-called small q, and go through the Brillouin zone from one lattice point or high symmetric point to the other one. You can see here easily how the scattering triangle changes while changing the q vector on this bow. And performing these scans, you can either do scans along q with a constant energy, which hopefully gives you this nice Gaussian peak, and every maximum of the Gaussian peak now gives you 1 point in this dispersion relation, which is finally the energy over Q. If the dispersion is not as stiff as shown here, you can take the other strategy. You change the energy at a constant Q vector, and again you have this nice peak and hopefully get a single point in your energy versus Q relationship. This is invented already in the 60s, and it's still the same principle in our days, probably with some better understanding of resolution effects and some technical tricks. So what is this useful for? You want to measure a dispersion and you want to learn from it and apply some models to calculate the interatomic forces. This is, and as I said at the beginning, you want to calculate properties of your material. But in addition, you can see here in the example of the shape memory alloys that you also have significant changes of these phonon dispersions when you, for instance, have a phase transition here, or in the other case of the classical superconductors, characteristic softenings or changes in the dispersion if you compare with a, in this case, non-superconducting compound, which are related to interactions of the phonons with other partners. And I will go through now through different examples to simply to let you know what you can do with this, with the result of this technique and what you can learn from it. For sure, it's only examples. There is a quite large variety of use of the spectroscopy in lattice dynamics and in magnetism. And I will start hopefully with an impressive example, which is the very simple elementary iron. For a long time, it's known if you come from the melt in iron, you start with a BCC structure, which you can see here, and this is a so-called delta phase, followed by an FCC structure, the gamma phase, which is the optimal solution for this crystal lattice. And if you cool further down, then again you come to a BCC structure, which is already unusual. But it was understood for a while that this is due to ferromagnetic contributions coming from local moments already before the sample orders ferromagnetically at a transition temperature, at the Curie temperature. But up to some years ago, it was not understood why we have this BCC structure at high temperatures before we go to this optimal structure. And some measurements have been performed in front of 2014 by a group at MLZ. And it was the first time that at these high temperatures, the phonons in the delta phase have been measured, and they have been compared with the other phases to find out what is the origin of this unconventional phase. And what you can see here, comparing this alpha phase with the unconventional delta phase, is that we have at the end point a high symmetric point, and in the direction of HH to the gamma point a softening of the phonon energy, both for this blue and for this green phonon. And in addition, we have an additional density of phonon density of state, which is also related to these kind of energies. And if you apply now the Born-von-Karman model and you calculate the force constants, and from this you go on and calculate the thermodynamic properties, you can easily find that there is a vibrational entropy, additional entropy, which stabilizes this high temperature phase in iron against the so-called optimal solution, which is lost at a little lower temperatures. For sure, you can also analyze all these other phonons, but I will not go into detail here. But I find it quite interesting that in the quite late times, in a very obviously very easy system, there are unsolved problems which need modern techniques to be solved. And the other example is our shape memory alloys, where we have structural transitions by heating and cooling, which are reproducible and find many applications in industry and medicine and many other cases. And one wants to understand this mechanism on microscopic scale to improve this material, probably for new or different applications. You can see here the temperature dependence of the Bragg reflections. You see that there are some transitions, first between the different martensitic phases, and also between martensitic and austenite phase. And this number combined with an M is a sign that we have a modulation in this martensitic phase, which goes to coupling of the 110 planes, which leads finally to a lattice distortion. And the precursor of this distortion you can see here in the temperature dependence of the phonons of this transferred acoustic phonon, where you can see the temperature dependence here. And if you come from a 5 times modulated structure to the austenite, you see an impressive softening of this transverse acoustic phonon. If you now compare again the modulated structure with a non-modulated structure, then you easily can see which are the phonons which have additional features. Some of them split, and this is related to a deformation of the cubic cell. The distance between these 110 planes is shortened, and in consequence, one of the phonons is hardened, and the other one, which I showed you now, is softened. So you can easily see the representative of these structural changes in the lattice vibrations, and comparing with compounds which have no modulations and no these additional effects like the shape memory effect, you can conclude about the origins of your properties. Coming back to the superconductivity, it's well known that there is a coupling between the phonons and the electrons, which are responsible for the superconductivity. So this softening here is accompanied by a change in the line width of the phonon, the full width half maximum. And BCS theory well describes the increase of this line width as related to the electron-phonon coupling constant lambda. So there is a dedicated branch of the neutrons responsible or contributes to this superconductivity. The lessons we need to learn is neutrons cannot see the electrons, so neutrons are normally blind for superconductivity. So in the classical case, we can learn about superconductivity by measuring the phonons and knowing about the strong electron-phonon coupling and performing calculations to understand the superconductivity. In the unconventional case, again, we cannot measure the superconductivity directly, but unconventional superconductors have quite impressive systematics. All these superconductors have parent compounds which are magnetically ordering. And if you suppress this magnetic ordering, we find superconductivity, as you can see here in a phase diagram. You tune your system by either the pressure or the stoichiometry and doping or the magnetic field, and you decrease the transition temperature into a magnetic ordering phase, here in this case an antiferromagnetically ordering state. And when the magnetic order vanishes, we have exotic phenomena, and one of these exotic phenomena is the superconductivity. There is a quite large variety of systems and a large variety of such phase diagrams with a gap between the magnetic phase and the superconductivity, or overlapping or additional other phases in between. But at the end, you can have a systematics between all these different compounds, which show this is the superconductivity, which is not related to phonons. This is first the heavy fermions with quite low transition temperatures and quite different, but mainly layered structures. We have the cuprates, which have quite high transition temperatures, more complicated structures, and again, some kind of layering if you have a look. And the iron-based superconductors, which are again in a quite large variety of crystal structures, but showing some layering and intermediate transition temperatures. And all this systematics shows that the crystal structure is nothing which is related to the superconductivity, but with neutron scattering, with inelastic neutron scattering, we find one feature which all these compounds show. If you go to the non-superconducting, the paramagnetic state, you can see in the excitation spectrum, which is intensity over energy, at a point where we finally in the ordered state would find the magnetic propagation vector. But we are in the non-ordered state now, but we choose just this position in Q where the ordering would occur if we would order magnetically, and we have a quasi-elastic scattering here on the energy gains loss side of the neutrons. And if we cool down now, to the superconducting state, some intensity of this quasi-elastic scattering condensates in a pure inelastic peak. And this is a feature which is to be shown, or which occurs in all these superconductors, for sure at different temperatures related to the superconducting transition temperature. But again, we are blind for superconductivity. But what we see with neutron is the magnetic response. So we have a probe now to see a magnetic signal. And what we learn from that is that this kind of superconductivity is definitely related to magnetism. And now we can start to find the overall feature, which is in all these different compounds with all the different spectra and all the different structures, to find out about the origin of the magnetic excitations and the relationship between these magnetic excitations and the superconductivity. Going along go further into magnetism, inelastic neutron scattering is one of the points where we very often have search for new interesting or exotic ground states. One example here is pure basic research, the prototype of a so-called ideal square lattice, which is a strontium copper boron oxide compound studied by a Swiss group. We hope to have here a model system where this square lattice, the 2D square lattice, is grown in a crystal. And what you see in this sketch here is that two copper atoms couple two dimers. And if you have these dimers and you are at low temperatures and low pressures, then you find two excitations, which you can see here in this red curve, which change with pressure. And it was proposed by NMR measurements that at high pressures there is a change of the ground state into a new unknown ground state, which cannot be explained by these measurements. And what is done now in a couple of experiments at several instruments is to find out about the magnetic excitations in the system. And what you see here at roughly 17 kilobar, you have a structural, or you have a phase transition, which is related to the loss of the high energy excitation. The low energy excitations survives but changes its energy, and we have a new excitation, a so-called low energy excitation, which you can see here in the measurement very nicely, which vanishes at high temperatures. And this is related to this new stage, which is a so-called plaquette state. You have, in addition to the coupling between two copper ions, coupling of 4 of these atoms, or the magnetic contributions of the atoms. And now, with knowing these excitations and additional information, you can calculate this ground state and explain what happens at the phase transition. New ground states are also related to either non-ordering or weakly ordering compounds. One of them is, or one origin of this weak or non-ordering phenomena is the frustration, either due to geometry or due to other reasons. And I show you here an example of a 3 sublattice magnetic structure, where you see that within this triangular lattice, it's difficult to find a way to order all these magnetic moments. Finally, we come out with this 3 sublattices plus a multipolar order, which is characterized here by the lines. And the characteristic spectrum here is, this is time of flight measurement now, is a little away from the normal spin wave behavior. You can see it's quite complicated, but still to be calculated. These calculations have been done, and they lead to the prediction of the Bragg positions of these magnetic structures. You see here a Bragg reflection measured with quite normal high intensity, what you expect. But at the gamma point, the magnetic intensity is very, very weak. And you see here that this is possible to be measured only at a triple axis spectrometer, having some, putting some effort in to have low background to get this quite weak intensity. And another exotic ground state is measured by a group from Berlin, where we have a quasi 1D magnetic ordering in a Heisenberg magnet, strontium copper vanadate. A characteristic spectrum of these low dimensional magnets is the quite extended continuum, but with a very sharp border to no signal in the Q omega space. We have a spin half chain in this magnetic insulator, but if you cool down, then you see that our continuum is lost, and we have a spin wave kind dispersion. But going into more detail with high resolution, you see that the energy scan over Q gives you a kind of oscillation. And having an analysis and some calculations about it, the group decided that we find, by cooling down, a coupling of the spin half moments to a spin 1 moments, which can be related to something which happens also with particles with fractional quantum numbers, which form quasi-particle with integer quantum numbers. So the effect is here named a confinement, a spin confinement. And last but not least, you can have a coupling of phonons and magnetic excitations, which we could show in the work of Petter some time ago. We have here a picture of energy over reciprocal space, and we have some phonons along the different crystal directions. And we have the crystal electric field, which is a dispersionless magnetic excitation due to the local moments at the at the rare earth place. And what happens now if the crystal field and some of the phonons have the same symmetry and the same energy, that the interaction gives surprising phenomena, which can be a bound state, an additional excitation of quite weak intensity, or an anti-crossing of the related phonons, and possibly also an exchange of the character of the phonons. So far to the examples, I'm more or less in time, so I wanted to interest you with these examples in joining us for spectroscopy or making use of this technique to learn about a lot of interesting and nice phenomena in magnetism and lattice dynamics. And due to the title of the mini school, I want to give a few words about a fair data management. I have a paper on the left-hand side. You can see a paper from 2019, and what is written there is, as it was done all the years before, if you want to make use of the data, please ask the author of the paper. And very often the author changes the field and the data are lost. One of our last papers has a different remark. Our data have a DOI as well as the code. Please make use of it and check what we did. And I like it very much, since it gives us the chance to not only to check and to prove what the colleagues did, but also to have another access and try to come with new ideas onto old data and improve the outcome of these neutron experiments. To do so, for sure you need a set of metadata. You need to have a set of data which you can use, since you understand what is done there. So one needs every information around the measurement, the sample itself, and during probably the experimental procedures. And we invite you to join the discussion about this metadata agreement within a project on 3-axis spectroscopy, which we will start soon and which will hopefully be funded within the Daphne proposal. Other aspects of this proposal are software catalogs, where successful codes will be probably collected and provided for beginners or for less experienced users to apply these codes onto new experiments for sure on base of metadata and data structure agreements. And it would be very nice if we could find old data or related data to avoid additional or double experiments. So we applied for this funding, but anyway, we will do so with the resources we have. So please join a discussion on that, or join with ideas, and maybe also the team. Thank you very much for your attention. I collected some references, but for sure, greetings from Panda, and thank you for your attention.